Yeah, the next topic is how temperature affects atomic spectroscopy. We've already learned that in atomic spectroscopy, atomization is very important. Okay, but after atomization, no, we can do the absorption measurement or emission measurement, and then how, let's see how temperature affects, okay, the those spectroscopies. Okay, let's first consider the extent of atomization. Okay, um, usually, electrons in atoms mostly reside in lower state or ground state, and then if you increase temperature, and then by the thermal energy, the electrons are excited to upper state. Okay, and let's see how or how many in or how many percent of electrons are excited. Okay, here is a very famous the theory, which is Boltzmann distribution theory. Okay, Rudolf Boltzmann showed that uh, this population distribution depends on the energy difference. Okay, it is exponentially decreased. Okay, for example, n0 is the number of electrons uh, in ground state. Okay, and then here in this case in this ground state there are two identical states. Okay, so in this case G0 is 2. Okay, and then the first excited state there are three identical states. Okay, and then the energy difference between the ground and the first excited state is delta E. Okay, and then population electron population on this excited state is n star. Okay, and then the ratio of n star n0 is given by g star divided by g multiplied by exponential minus this energy difference divided by kt. Okay, this is such a famous Boltzmann distribution. Okay, so temperature affects in the population of excited states. For example, in the case of a sodium atom, the lowest excited state, okay, per atom, it is the energy difference is 3.371 times 10 to minus 19 joule per atom. Okay, for a single atom at 2600 Kelvin. Okay, in this case, G star is 2 and G0 is 1. Okay, so what is the ratio, yeah, between the excited and ground state population? Okay, and here we use this Boltzmann distribution, and then we get 1.67 times 10 to minus 4. Yeah, this is quite a small number, less than 0.02%. Okay, let's assume, yeah, we increase temperature by 10 degree Kelvin. Okay, just a 10 degree C elevation. Yeah, and then using this you know temperature here, using new temperature, we get 1.74 times 10 to minus 4. Okay, which still this number is quite small. Okay, but what's the difference? Yeah? How many percent increased? Yeah? Here, take a difference and then divide by 1.67, and then this is 4%. This is implies a significance because the temperature increased by only 10 degrees C makes the population in the excited state increased by 4%. Okay, 4%, but still it's very small number, but increment is 4%. Yeah? But the population difference on the ground state is negligible. Okay, because it's a very small amount uh, difference. Okay? Which means that by increasing temperature, atomic absorption yeah, may not be the sensitivity may not be greatly increasing, but atomic emission will be greatly affected by temperature. Okay, so temperature effect on absorption and emission. What the effect is much more on emission than absorption. Okay, here 10 Kelvin temperature difference doesn't affect much on ground state population. Mm, okay, so the atomic absorption signal is not much affected. Okay, but excited state population increased by 4%. So emission intensity will increase by 4%. Okay, yeah. So that's why atomic emission is much more sensitive than atomic absorption. Mm. And also now, if we use ICP, then the sensitivity will be even greater. Okay. And look at this table. Yeah, this table says the effect of energy difference and temperature on population of excited states. Okay, here this is the wavelength difference. Okay, wavelength difference. That means we can can translate this wavelength difference into energy difference, joule per atom. Okay, and here I put my calculation. Okay, for example, 250 nanometer wavelength difference is corresponding to this much energy difference. How? You see, to translate into this one, my way of calculation is to consider electron volt. One electron volt is 1.602 times 10 to minus 19 joule. Okay, and electron volt and wavelength has this relationship. Okay, from this electron volt we can get nanometer. Okay, or from the nanometer we can get electron volt. For example, 250 nanometers corresponding to 4.696 electron volt. Yeah, why? Here we simply divide this number. 1239 divided by 250 is 4.696 electron volt. Okay, and then simply by multiply the electron charge, which is 1.0602 times 10 to minus 19 joule, and then eventually we get this number 7.94. But here I don't know why it's 95. Okay, but it's almost the same, times 10 to minus 19 joule. Okay, likewise you can calculate the this wavelengths in nanometer into energy difference in joule per atom. Okay, and then this one, excited state fraction. Yeah, n star over n0 could be calculated using Boltzmann distribution, depending on the temperature. Okay, so now you see this one. Okay? At high temperature, the population of excited states becomes larger and larger. Okay, and this one, this column is obtained by flame. But this one, 6,000 Kelvin, could be achieved by ICP plasma. Okay, and in this case, at 6,000 Kelvin and energy difference of 750 nanometers. Okay, and then the excited state population is 4.1%. Okay, this is great number. But for halogen atoms, like fluorine, chlorine, bromine, and iodine, energy levels are so high it emits ultraviolet radiation below 200 nanometers. Okay, yeah. And then this one, the radiation, electromagnetic radiation, whose wavelength is below 200 nanometers, is called vacuum ultraviolet. Okay, why vacuum? Yeah. So this wavelength is so small, so this electromagnetic radiation cannot pass through the air. Why? That's because this electromagnetic radiation now scattered by air molecules. Okay, that's why uh, uh, we um, we need to make the the spectrophotometer inside the vacuum. Okay, for this far ultraviolet radiation, right? Because in the presence of air, this electromagnetic radiation is scattered much, so signal will be very weak. Okay, so spectrometers for the far ultraviolet were customarily evacuated. Okay, some plasma emission spectrometers are purged with nitrogen to exclude air, so that the region 130 to 200 nanometers is accessible, and chlorine, bromine, iodine, phosphorus, and sulfur can be analyzed. Okay, so those elements, these halogen atoms or phosphorus and sulfur, their uh, emission line, yeah, is below 200 nanometers. Yeah? So the chamber uh, should be purged with nitrogen or should be evacuated. Okay, and let's keep going. Let's now consider the line width, okay, of emission line. Okay? Atomic line width is radiation source of line width is what smaller than the line width of absorbing sample. Okay, in order to apply uh, Pierce law. Okay, otherwise, the Pierce law, cannot be applied. Yeah? So requirement is that atomic the radiation source line width must be much smaller than line width of absorbing sample. Okay, otherwise the radiation source, the radiation, much of the radiation may not be absorbed by the sample. Okay, so very fortunately, the intrinsic line width of atomic absorption is about 10 to minus 4 nanometers. Wow, wow, this is very, very narrow. Okay, but uh, there are several mechanisms for broadening of a line width. Okay, actually, line width, the smaller the better. Line width is governed by Heisenberg uncertainty principle. Okay? Just assume that from the physical chemistry, you've already learned the hydrogen uncertainty principle, or in general chemistry, you also learned the Heisenberg uncertainty principle. Okay? This principle actually means that you cannot determine the the momentum and the position at the same time, yeah? Or you cannot determine the time and energy difference, yeah? With infinite precision. Yeah? That's impossible. Yeah? That's the Heisenberg uncertainty principle is the one of the very basic principles of quantum uh, mechanics. Okay, so this principle says the the error in energy and error in time, the product is all the time is greater than this constant, this h over 4 pi. This h is what? Planck constant. This h value is very, very small actually. This one h is 6.62 6 times 10 to minus 34 joule second. I strongly recommend you memorize this constant. Okay, yeah, this is very important. Okay, now we are dealing with the line width, and line width is related to the energy difference. So energy difference or energy, the error in energy is all the time greater than this one, h divided by 4 pi delta t. Okay, here delta t is what? Delta t is a lifetime of excited state. Okay, delta E is energy difference. All right. Yeah. So when if the electronic lifetime of in the excited state is 10 to minus 9 second, and then we can easily get the delta E value, which is 10 to minus 25 joule. Okay, still this is quite small. So if um, the wavelength is 500 nanometers, okay, and then uh, that is corresponding to, let's say, the energy difference between ground state and excited state. And then we can easily get the delta E, okay, using by this equation, this Planck equation. Then the delta E is 4 times 10 to minus 19 joule. All right. Yeah. So relative uncertainty in energy is what? We divide this value by this one, okay? Energy difference. Then we get 2 times 10 to minus 7. Wow, very, very small. All right. So uh, the line breadth, okay, line width can be calculated using this equation. Delta lambda divided by lambda equals delta E divided by this large delta E. This is all the time greater than 2 times 10 to minus 7, this value, okay? And delta lambda is this number multiplied by lambda. Lambda is 500 nanometers. And then this inherent line width, okay, is 10 to minus 4 nanometers, okay? This is quite small number actually, right? This is inherent because this Heisenberg uncertainty principle is inevitable, yeah, unavoidable. Okay, we cannot, you cannot beat this principle. Okay, this is that in the sense is inherent. Okay, and also there are another line broadening mechanism. Okay, you see, the emission line should be, as sharp as possible, but the intrinsic line broadening mechanism is depend on due to the Heisenberg uncertainty principle, and another mechanism is the Doppler effect. You know the Doppler effect. Doppler effect says the frequency when the moving objects you know, moves toward you, and then that frequency increases, or if the moving object is what is moving away from you, and then you feel the frequency is decreasing. Okay, that's the Doppler effect. Yeah, using this Doppler effect, um, yeah, we can estimate the what the distance. Okay, so Doppler line width is given by this equation. Yeah, I don't know how this equation is derived. Anyway, delta lambda approximately is lambda multiplied by this term, 7 times 10 to the minus 7, and square root of T over M. Yeah, T is temperature in Kelvin, M is atomic mass. Okay, for example, for iron atom at temperature 2500 Kelvin, and the atomic mass of iron is 56. And then let's say if lambda equals 300 nanometers, and the line width delta lambda is 0.0014 nanometers. Okay, still maybe okay. Yeah, very narrow. Okay? Another line broadening mechanism is pressure broadening by collision. Okay, when collision takes place, the lifetime of excited state becomes short. Okay, here from the this Heisenberg principle, if delta t is short, okay, and then delta e becomes longer, okay, the larger. Okay, so collision makes the excited lifetime short. As a result, um, line gets broader. All right. Yeah. So what? Working in a low temperature has advantage. All right.